this slide, not yesterday, last 2 days, Sunday, we stopped at this slide. Okay, this is another type of the crystal structure, okay, other than cubic structure. Okay, for HCP, we call it hexagonal cross pair because of the top surface shows hexagonal pattern. Okay, if we look at this atomic structure, the crystal structure, not atomic structure, sorry. Apa yang bising dia? Please mute your microphone. Alright, thank you. Okay, so if you look at this, right, these green atoms is forming the hexagonal structure at the top surface of this crystal structure. Okay, one atom is located at the 12th top and bottom face corner of the hexagon. Okay, so here containing one atom. Okay, this one containing one atom, another one atom. Okay, right. So one atom at each center face here. Okay, the blue color. All right. So this one is half atom. This one is half top and bottom, and 1/3. So 1/6. Okay, 1/6. So we have a 6 at this corner. So it is equivalent to one atom at the top and another one atom at the bottom. Okay, so now how many atoms accumulate atomic volume from the blue and green atoms? What is the total atoms?
Three.
3. Okay, because the green we have 6 at the top, so this is equivalent to 1, and this is another 1/6 multiplied by 6 at the bottom. So this is equivalent to 1, this is equivalent to 1, this is multiplied by 2, top and bottom, so equal to 1. So 1, 2, 3. Okay, 3 mid-plane interior atoms. So altogether is 6 atoms. So the example of this kind of structure is such as the zinc, cobalt, cadmium. Okay, so there are different in terms of the crystal structure inside this kind of elements. Okay, so if they are stacked together, forming an ordered structure, okay, whatever you see the zinc structure, the physical zinc structure, inside the zinc is actually there are atoms arranged such this way, okay, in the HCP crystal structure manner. All right, so this is a 1/6 portion of atoms. Okay, this is half. Right. So this is one single atom, 1 multiplied by 3 atoms. Okay. So we have 12 at this 6 hexagon corner. So we have 2 and 1 at the face and 3 at mid planes. So altogether is 6 atoms for the HCP. Okay. To forming one structure, there are 6 atoms. All right. So for this kind of structure, okay, if we calculate the atomic packing, how packed this structure, okay, in terms of the volume of sphere or the atoms, okay, imagine one atoms, not imagine, we assume one atom forming hard sphere, okay, so that's the reason we measure the sphere for to determine determine the atomic packing fraction, all right, or factor. And then how packed it is one cell, okay, we call this cell, unit cell, is we need to divide it by the spaces for this type of cell. So it is equivalent to 0.74. How you determine this? There are one constant called C over A equivalent to this value. Okay, C over A equivalent to this value. What is C? This is C. This is A. So this is also A. Okay, so it is hexagon. So every side has a similar constant, which is A. Okay, or let this constant we call it. Okay. So the coordination number of one single atom 1, 2, 3, 4, 5, 6. Okay, they are attached. Then this maknanya one that's mean every one single atoms it was surrounded or touching this atom. So we call it coordination number. Okay, and then at this side also it's coordinate with the 7 atoms. Okay, 8, 9, 10, the other side. Okay, and multiply by 10. Okay, 1, 10, 11, 12. Okay, so it has 12 coordination number. So one single atom, it will touch with these 12 atoms. So coordination number for HCP structure is 12. Okay, this is coordination number. So the FCC and HCP structure both have atomic packing fraction of 0.74 and coordination number of 12. Okay, the difference between this is the stacking sequence. Okay, A, B, C, A. Okay, that is sequence A, B, A, B. So they are different sequence, different structure. So another terms that we need to consider in the crystal structure is allotropy. Allotropy is the property of some chemical elements to exist in 2 or more different form of crystal structure. For example, carbon. Okay, so they are all these are different structure of carbon. Okay, carbon if it's forming like this one, we call it graphene. Okay, if it's forming like this one, we call it what? Apa ni? Yes, graphite. If it has a very complex structure, it's forming diamond. Okay. All right. Electrodes. Okay. You don't have to discuss. This is Simon said by Dr. Habibah. Okay. About the electrode for iron. Okay. Let me show you when we talk about electrode of iron. Okay. Iron, carbon, is okay. You are going to learn this at chapter 5. So I'm going to show you this as a all right. Okay. This is a phase diagram. Okay, what is phase diagram? You are going to learn this in material science lab. bila akan masuk nanti you all belajar dengan saya juga kan, skema I section 9-10. So you are going to do your lab, I think ada instruction. So this is iron carbon first diagram. What is x-axis which contain carbon, capacity X, and y-axis is the temperature. Okay, meaning that composition of carbon will increase from left to right. Okay, most left, top left is 0 carbon, so it is pure iron. Betul tak? Is it true? The value at x-axis, capacity X, at a 0% of carbon means this alloy is pure iron. Is it true? All right, look at the pure iron. We talk about electron. Just now, I have mentioned about electron. So meaning that it's contain different structure. Okay, like a graphene, like carbon. It's a chain from graphene, and then to the there's also a graphite. There are also carbide. Okay, so there are different electron. Okay, so for iron, okay, for pure iron, if you look at for pure iron, all right, at 0 until all right, for this kind of iron, all right, okay, from 0 until about 900 degrees Celsius, or at the G level here, 911, okay, it will change from what we call it, this alpha structure, alpha, okay, alpha structure, you can see symbol alpha, right, to the gamma structure, this one, this guy. Okay, at what temperature? 911. And then if you go further to the top at 1400 degrees Celsius, it will change another symbol, which is delta. You can see delta ferrite here. And then above that at 1535 degrees Celsius, okay, it is melting temperature. Okay, it is melting temperature. So, okay, so maksudnya macam ni. If you look at the weight percentage of carbon for the first diagram, and this is melting temperature, okay, at 0 until 911 degrees Celsius, at this condition, it is in the alpha structure, okay, call it ferrite iron. So at this structure, it is BCC, body-centered cubic structure. Okay, remember we talked about BCC last time. Okay, so this is iron, still iron, pure iron. I'm talking about 0% of carbon. Okay, I'm talking about this composition. All right, so meaning that our material is pure iron. So 0 until 911, okay, it will change from alpha to gamma iron. So it is still pure iron. But for this guy, it is FCC structure. Okay, and then if we look at, okay, at what temperature? 1392. Okay, 1000 at this temperature. Okay, this to this, it will change into gamma. Okay, 1390 degrees Celsius. Okay, until 1500 something, it will become delta structure. Okay, so for this structure, it will change into delta iron. It is still pure iron, but it has BCC structure. Okay, and then above 1500 something, it will become liquid. So this is electron. Okay, it will change its structure based on the temperature. Okay, so this is what okay, this is actually the answer for this homework. All right. So there are another one thing when we talk about crystal. It is a single crystal. Okay, what is single crystal? It is an ideal single crystal has has an atomic structure that repeats periodically across its throughout its whole volume. For example, if you have one material, whatever lah material, misalnya kata this material lah, cakap apa, contoh lah, okay, the whole structure from here to throughout its material, the atomic arrangement is only one type like this. Okay, if it is FCC lah throughout the structure. If it is BCC continuously, all right, continuously throughout its whole volume. At infinite length scale, okay, infinity length scale to imagine at the scale of atom. So kalau panjang di 10 cm pun dah consider as infinite because it is so long for the scale of atoms. Okay, and it's no symmetry. Okay, for the whole volume of the particular component. Okay, this is single crystal. What about non-single crystal? Non-single crystal is we call it polycrystalline. Okay, this is opposite to single crystal. Okay, polycrystalline or polycrystal is comprised of many individual grain. Okay, inside the grain, there are the crystal structure, which is FCC or BCC or HCP or whatsoever. Okay, whatever the structure that, but it's contain grain. So meaning that, okay, for example, this is let's say this is FCC. Okay, FCC is happen continuously until this limit, and then there is another FCC at this region. There are another FCC at this region. Okay, of course, one region, or we call it grain. This is one grain. Okay, of course, inside the grain there are millions or billions numbers of atoms. Okay, this is just a schematic diagram. Okay, so meaning that inside the grain, the atomic structure forming FCC or BCC or HCP structure. So, but polycrystalline is contain grain. Unlike the single crystal doesn't contain any grain. Okay, it is very perfect. Perfect memang canggih dia nak produce single crystal. Okay, so each grain can be true of as a single crystal within which the atomic structure has long range order. Okay, jadi saya cakap lah, maksudnya it is not only 10 or 12 atomic or crystal structure, very long. We cannot calculate how many crystal structure inside. Okay, the interface between the two grain, we call it grain boundary. So here is a grain boundary. Okay, the interface, meaning that the boundary between the grain, we call it grain boundary. Okay, this is grain boundary. All right, so now we have talked about single crystal and polycrystal. Okay, so single crystal, okay, for example, I give you example of a single crystal. If we type the application, okay, single crystal. Look at this Google result search. Okay, But you can see single crystal turbine blade. Why? What do you know? Do you know what is turbine? Do you know what is turbine? Tahu tak turbine? Untuk generate energy lah kan, combustion kan?
Generate energy, yes.
Okay. So macam jet engine. For example, the jet engine like this. Okay. The two spherical or cylindrical or almost cylindrical shape at the two wings of the airplane. Okay, this guy. Inside this, okay, inside this turbine, there are hundreds of blades. Okay, like this one. Okay, you can see there are a lot of blades inside. And if we extract, okay, from this image, this is one single blade. So how they produce this blade? It is a single crystal structure. Okay, single crystal. To produce this, they use a very specific method, and they have to ensure that this one has single crystal. It shouldn't contain a grain boundary. Okay, why? Because the grain boundary is actually a weak point. Okay, weak point for the first failure or starting point for the failure to occur. So in order to eliminate failure, they have to ensure these turbine blades is formed or fabricated in a single crystal. Why? Imagine turbine. What is the operation? If you travel from anyone here from Middle East? Anyone?
Yes, doctor.
So how long it takes from here to from Malaysia to your hometown?
It's about 9 hours by flight.
Wow, by flight 9 hours. Where is it? Your hometown?
Saudi Arabia.
Saudi Arabia. So 9 hours. Imagine these planes need to operate. This blade will rotate. The turbine operates for more than 9 hours, and the blades will rotate, do the heavy works, and the temperature maybe reach up to 1000 degrees Celsius. So force being subjected to these turbine blades rotating. Okay, cyclic loading is very too much on the blade, so they have to eliminate what? Eliminates this grain boundary because it is a weak point. So there are two different crystal. Okay, both are crystal. One is single crystal, one is polycrystal. Polycrystal is easy to produce. If you have a liquid and you want to solidify it, just do, you can design how many grain boundary you want. Too much grain boundary, less grain boundary, okay, small grain, large grain. However, for single crystal, it is very critical process. And why? Because they want to design something less potential for failure. So there are two different crystals actually. But inside the crystal, yes, they both can contain FCC, PCC, or whatever crystal structure. Okay. So I think that's all for the this part of this lesson. Okay. So whatever you have to know is actually something to do with the structure of the unit cell. Either it is PCC, FCC, and then what else? We talk about FPF and also the density, coordination number, single crystal, and polycrystal. Okay. So the next. All right, this one, I think we need to do a lot of exercise. So please do not miss tomorrow tutorial class. Okay, we have 30 slides, but okay. All right. In this topic, you are going to learn how to give an index by direction of the plane for the crystal structure. Okay. first what you have to know, because this kind of system is important in order to relate with the properties of the material. Okay, for example, like here, one method of plastic deformation is by dislocation slip. Okay, so meaning that if you want to change the shape of one solid materials, okay, you need a behavior of plastic deformation. Okay, so if you want to bend a rod metal, for example, or metal plate, um, uh, the material will experience plastic deformation. Plastic deformation is permanent deformation. So meaning that after you release the load for deformation, the shape will unable to reverse its original shape. So understand the lattice planes and direction is essential to explain why this location move, okay, combine and tangle in a certain way. So some material properties such as electrical and thermal conductivity, elastic modulus can vary with a direction which indexed by a system. Okay, so you are going to learn about this system. Okay, for example, this is a FCC structure. Okay, this is the FCC structure. So okay, so the when we give a load, okay, when we give a load, the atoms are have a certain tendency to move based on the crystal structure. Okay, uh, this is the in this direction. Okay, look at this direction. Okay, uh, okay. This direction compared to, let me see, this direction. Okay, direction A, A and direction B. If you look at the, so meaning that the energy, so meaning that if they receive a load, they are is it, okay, he don't want that the loads that subjected to during the application of the turbine blades that allow the atom easily move following the direction of the load during the service. So you need designs somehow that this take consider the direction of B, okay, where the load of circuit loading consistent to the direction of B, and he avoids that the direction of load from during the service, the circuit load. Okay, he avoids the position of design structure following the direction of A, because if it's so, meaning that the materials, the atoms inside the turbine blades is easy to move, meaning that the structure will easily change in shape. So that's the reason the direction inside the crystal structure is very important to understand. Okay, and to understand that, they create a system that called Miller index. Okay, this direction and plane can be described with Miller index. Miller index are a method of describing the orientation of a plane or set of planes within a lattice in relation to the unit cell. Okay. Okay, for example, like this one, this is the origin. Okay, 0 is the origin. Okay, um, when we talk about coordinate, okay, it's similar with the map coordinate, something like that. Okay, and for example, position A. Okay, so remember, for this system for crystal structure, the x is this direction, y is this direction, and z is this direction. Okay, so please remember this. Do not confuse with other courses. This is only special for materials science. Okay, so if we write the coordinates still the same, x, y, and z, and coordinate we have a comma between the coordinate. Okay, right. So x, of course, coordinate, because this is unit cell, the simplest, the most smallest distance, we call it, from 0 to a. So from 0 to a, there is no other spaces. Okay, only one. Okay, 0a is considered as coordinate 1. So x for point a is 1. And then y for point a, okay, this point a doesn't move any at position, is not move to the y direction, so it is considered as y equal to 0. So x equal to 1, y equal to 0, and z, it doesn't move to upwards, so z equal to 0. So that's the reason we got, okay, 1, 0, 0. And for b, if you look at b, okay, so b position at y direction is, this is y direction, so y equal to 1, whereas x and z is equal to 0. Simple je, sangat senang. This is so much easy. Okay, this is only coordinate, nothing to do with the index million yet. Okay, right. So c, if you look at c, yes, it is equivalent to 1 at z direction and 0 for all other direction. Okay, and the rest. All right, so if you look at h here, this h, okay, from this point to h direction. Okay, so this point, okay, to most to h direction, okay, if we can draw based on the xy, if we can move step by step from x, y, and z, okay, you can see that it's moving half to x direction, and then all the way through to y direction, okay, y direction until this, and then it so meaning that the first moving x equal to half, and then y equal to 1, and then it's go up here until it reach h point, is z equal to half. So the coordinate is half, 1, half. Okay, this is only coordinate. All right, so the direction, okay, to determine this direction, okay, the system formula index, okay, we call we give the value HKL. Okay, what is HKL? HKL is the distance for x, y, and z. Okay, so there is one method. Okay, the method is first we need to get the coordinate. Okay, coordinate for the for this arrow. Okay, which is the tail. Kalau ni anak panah kan, this tail, this is arrow. Oh, bukan arrow lah, head. All right, head and tail. So you need to obtain the coordinate for head and tail. What is coordinate for F? Can you guess? F, what is it? Correct. So meaning that it moves to the front with the position of half, and then it moves to the right with the position of half, and it moves upwards with the distance of 1. Okay, so and the tail is 0, 0, 0. Okay, right? Okay, so if you look at here, it's moved to the front with half step, half directions, to the right half, and then 1 at the top. Okay, so and then tolakkan, subtract coordinates. Okay, for head minus tail. So meaning that head minus tail. Okay, x with x, y with y, and z and with z. Clear the fraction. Write the integers in a square bracket. Okay, negative integer indicates by putting a bar over the okay. Right now, we look at this. All right, for here, head, tail. Head is half, and 1. Okay, tail is 0, 0, 0. This is H, K, L, oh, sorry, L or X, Y, Z. Okay, subtract, you can get half, 1. Okay, so the Miller index, okay, look at this. If we have negative, we need to put bar somewhere on top of the integer. Okay, write the integer first and square bracket. So to change this number into integer, we just multiply by 2. So what we got is 1, 1, 2. So we put the bracket. This is the Miller index for this direction. Okay, what is the answer? 1, 1, 2. Okay, there's no comma between the value. Okay, no comma, because this is not coordinate. This is not coordinate. Okay, so this is some exercise. You can do it, and there are example you can try by yourself. So first, okay, look at the direction for OA. Okay, OA, this one. Okay, right. For the head, what is the value for head?
100.
100. Tail 000. So easily you can guess the Miller index. What is it? 100. Okay. All right. And then let's try OD. Head. What is the head for OD? Okay. Head.
10 half.
10 half. Okay. Tail 000 lah. So what is the Miller index for this one?
201.
201. Okay. What about B? This one. 110. Are you sure? Okay, let's do it. Look at it. Head. What is the coordinate for head? 1. 1. 0. Good. Tail. Hey. Tail. For B. Oh, okay, sorry. CB. Saya silap. Okay, ni 000 lah. Okay. Alright, so 000. So the answer is 110. Okay, sorry. Saya silap. CB. Head. Huh? Salah lah. 110. Okay. Tail.
111.
1. So what is the coordinate for this one? Coordinate pula. Index, Miller index. Okay. So kalau kita lukis, kalau kita buat matrix macam ni, X, Y and Z, this is head, this is tail. So head is 1, 1, 0, 1, 1, 1. Subtract with what? 0, 0, minus 1. So the answer is 0, 0, 1 bar. Okay, remember minus. Okay, we put the cap on top of the whatever respective value for the index. So the answer is 0, 0, 1 bar. Okay, right. So where's the this one? Negative integers are indicated by putting bar over the integer. Okay, so that's the reason we got this answer. Okay, this one. Alright, this answer. Alright, senang eh. Okay. Alright, okay. This is the reverse reverse way how you want to draw the given Miller index. Okay. So for example, I'm not really sure. I think this one it has bar at the top of this. Okay. Right. Okay, let's start with the first one. Okay. Okay. One bar, 1. Okay. So all right. To do this, one, get it here. One bar, 1. Okay. Okay, tadi saya silap bracket dia patut macam ni bracket ni. Square bracket untuk direction. Kalau macam ni maksud dia ni adalah plane, ini adalah direction. Okay, sudah betulkan saya punya kesalahan tadi. So please make sure the square bracket is for the direction. Okay, this square is for the plane. Okay, so now we talk about the direction. Okay, forget about this one. Right. So directions, we have this. Okay, so what we have to do, we start with the origin, which is 0, 0, 0 coordinate. So look at the x axis, y axis, and z axis. Okay, y is 1, x is 1, y is -1, and z is 1. So what you have to do, create your axis first. This is x as positive and y in negative direction. Okay, y in negative direction and z in positive direction. Okay, this is origin. Okay, x positive, y negative, and z positive. So you need to first draw the cube inside this region only. Okay, quickly. Okay, and by acceptable and correct dimension of a cube. Okay, dimension or what do you call it? Pandai-pandai lah you belajar kan 3D image. So you should be able to draw a correct cube. Okay. Alright. So to draw the direction, you start with 0 here at the origin, and then it move positive direction at 1. Okay, you move here 1. This is 1. Okay, and then y -1. Okay, to this direction, go to 1. Okay, at y direction, and z is 1. Go upwards. Go here until here. So this is the end, the destination. Okay, so you need to draw a direction like this. Okay, this is origin, this is the head, and this is the tail. Okay, this is the tail, this is the head. So first you have to define the origin first, and then where to draw the cube based on this positive, negative, and positive XYZ direction. Okay, or axis. All right, and so once again, we still have about 1 minute. Okay, let's take a look at this example 250. Okay, 250 divide the largest index. Okay, divide by the largest index. Okay, so that the largest index will become 1. So from here you divide it by 5, and then you will get 2 over 5, 1, and 0. Okay, so all is positive. X, Y, Z is positive. So let's start with X. X from here to this direction is 2 over 5. Okay, you need to label like this, 2 over 5. And then you go to Y direction, Y equal to 1. So from this point to this point is equivalent to 1 scale at Y direction. Okay, and 0 for Z direction, so you don't have to go upwards. Okay, so stop at this position. So this is the what we call it, the direction, Miller index direction for 250 Miller index. Okay, so one more, let's try 1 to 1. Okay, last one, 1 to 1. Okay, 1 to 1, or maybe we can draw one okay, like this. Okay, so X is equivalent to 1 positive, Y is 2, and Z is minus 1. So if we draw the table like this, X, Y, and Z, okay, starting with okay, divided by the largest integer, which is 2. So you can get half, no, sorry, X equal to half, Y equal to 1, and Z equal to half. Okay, so you get this value. So now you want to draw, this is minus. Okay, Z equal to minus half. So start with the origin. This is origin 0, 0, 0. So X is positive. You draw the axis X. Y is positive, and Z is negative. So you need to draw a cubic within this axis. So how to draw this? Start with the front, and then the back, and continue connecting this corner. Okay. Right. So next, you need to draw the arrow. Okay, based on starting with half X direction. From here to here is half. Okay, label this so that we know that you stop at half, not through a 1 scale from 0 to X direction. This is X, and this is Y, and this is Z. Okay, Z, of course, negative Z lah. Okay, right. So from 0 to half at X direction, from here to Y direction at 1 scale. Okay, and then go down to half. Okay, how we want to label this? You can label half over here. So this is the head. Okay, the head, you draw the arrow here, you just connect this. Okay, so it moves to the front. Okay, at length of half, to the right 1, to the bottom half. So this is the the direction of your Miller index. Okay, so any question?